Somewhere at the very bottom of physics, there is a weight you could not feel. 21.76 micrograms. About the mass of a flea's egg. A speck you could hold on a fingertip and never know had arrived. Everything else down there is impossible to picture. A length 20 orders of magnitude smaller than a proton. A temperature of 100 million degrees. And then this one quantity, which is a piece of dust. That is not a coincidence. That speck is the reason there is a wall at the bottom of physics. A scale where general relativity and quantum mechanics stop working together, and where every calculation anyone knows how to do comes back as infinity. And it is built out of 3 numbers that no theory in the world has ever explained. Our understanding of physics has a limit. By the end of tonight, you will know exactly what that limit is, and why nobody alive can explain it. Before we start, if the slow way around a very large question is how you like to fall asleep, a like or subscribe would mean a great deal to me. It helps me keep making these. Now, let's ease in. Imagine you have been handed the job of building a universe from scratch, inside a computer, and you have been told that the finished thing has to be indistinguishable from the one you are lying in right now. Not similar to it. Indistinguishable. Same chemistry, same stars, same slow burn of hydrogen into helium, same weight of a coin in your palm, same color of the light coming through a window in the late afternoon. You have unlimited computing power and unlimited time. The only question is what you have to put in before you press run. The answer turns out to be shorter than almost anyone expects, and the shortness of it is the beginning of the problem. You would need the laws. That part is obvious, and it is the part everybody assumes is the hard bit. You would need the equations that describe how fields behave, how particles interact, how space-time curves in response to whatever is sitting in it. You would need the initial conditions, the state of everything at the moment you press the button, which is its own enormous unsolved question, and one we will set aside for tonight. And then you would need something else, something smaller and stranger and much harder to explain. You would need a list of about 24 numbers. Not equations, not principles, just values. Bare quantities that the laws you have already entered cannot produce on their own, that have to be measured out in the world and typed in by hand, because there is nothing in physics anywhere that says what they ought to be. The mass of an electron is one of them. The strength of the force that holds a nucleus together is another. There are 26 of them in the standard model of particle physics, and roughly 5 more if you want the cosmology to come out right as well. Enter them correctly, and the simulation grows into the universe you know. Enter one of them slightly differently. Shift a mass ratio by a few percent, nudge one coupling strength, and you may get a universe in which no atom heavier than hydrogen ever forms, or in which nothing at all clumps together, or in which everything collapses before it has time to do anything interesting. The laws would still be the same laws. The equations would be identical, letter for letter. Only the numbers you typed in would be different, and the result would be an empty room. It is worth making that concrete with the simplest object in chemistry. Take a single hydrogen atom, 1 proton, 1 electron, nothing else. To describe even that, to say anything at all about how those two things behave in each other's company, you need the charge on the electron, the charge on the proton, the mass of each of them, and the strength of the electromagnetic interaction that binds them. 4 or 5 quantities, for the simplest atom there is. Every one of them had to be measured. Not one of them can be calculated from anything more basic. The simplest thing in the universe already requires you to look the answers up in the back of the book, and there is no chapter that derives them. So here is the first thing worth sitting with tonight. The most successful description of nature that human beings have ever assembled, the Standard Model, which has survived every experimental test thrown at it for 50 years and has predicted quantities that were later measured to 11 decimal places, is a machine with about 24 dials on the back of it. We have determined the setting of every dial with extraordinary care. We have no idea what set them. That is not a gap in a textbook somewhere. It is not a matter of a paper nobody has got around to writing. Some of the best minds of the last 100 years spent decades of their working lives trying to derive even one of those numbers from something more basic, and every one of them failed. And we will spend some time later tonight with a few of those failures, because they are more interesting than the successes. But I want to be careful here, because there is a distinction hiding inside that list of 24 numbers, and this whole video turns on it. Almost every one of them is a fact about a thing. The mass of the electron is a property of electrons. The strong coupling constant describes how quarks and gluons hold on to each other. The neutrino mixing angles are statements about neutrinos and about nothing else. These numbers are fundamental in the sense that we cannot derive them from anything deeper. But they are local, in a way. They are settings on objects. If you had a universe with no electrons in it, the mass of the electron would be a number without a job. 4 constants are not like that at all. There are 4 numbers in physics that do not describe any object, any particle, any material, or any interaction between specific things. They describe the arena. They apply to everything, everywhere, whether or not anything happens to be there, and they are so familiar that most people who have heard of them have never noticed how odd they are as a group. The first is the gravitational constant, usually written as a capital G, which fixes how much curvature a given amount of energy produces. It applies to anything with energy, which is to say all of it, with no exceptions ever found. The second is the speed of light, c, which most people think of as a speed limit for photons, and which is actually something considerably deeper, the conversion factor between the time direction and the 3 space directions of the world you are lying in. It is there whether or not any light is present. The third is the Planck constant, h, which sets the scale on which the world stops behaving in the smooth, continuous way that everyday intuition expects. It shows up in every quantum equation ever written, without exception. And the fourth is Boltzmann's constant, K, which is the exchange rate between temperature and energy, and which applies anywhere anything is warm. 4 numbers about the room, rather than the furniture. And here is where it becomes genuinely strange, and where the question I want to spend the next 2 hours on actually starts. If you take 3 of those 4, G, C, and the Planck constant, and you combine them, not physically, but arithmetically, cancelling their units against one another until nothing is left but a distance, the algebra returns exactly one answer, not a range, one length, and it comes out at about 1.6 times 10 to the minus 35 meters. Do the same for time, and you get 1 time. Do it for mass, and you get 1 mass. For temperature, 1 temperature. Nobody chose any of these. No experiment produced them. They fall out of 3 numbers we cannot explain, the way a shadow falls out of a shape, and they are called the Planck units. And what makes them worth 2 hours of your evening is not that the length is small, although it is small beyond any useful comparison. It is what sits at that scale. That length and that time mark the exact place where our 2 great theories of the world, general relativity, which handles gravity and the shape of space-time, and quantum mechanics, which handles everything else, stop being usable at the same time. Push a calculation down there, and it does not give you a difficult answer. It gives you infinity, which is not an answer at all. It is the sound a theory makes when it has been taken past the last place it works. So our understanding of physics has a limit. That much has been known for a long time, and it is not really in dispute among people who work on it. What is in dispute, what nobody has been able to explain in 125 years, is what that limit actually is. Whether it is a real edge in the world, a place where space genuinely stops being smooth, whether it is a limit on us rather than on the universe, a boundary on what can be asked rather than on what exists, or whether it is neither, and it is simply where one description hands over to a better one we have not written yet. By the end of tonight you will know exactly what that limit is, why every attempt to explain it has failed so far, and why the answer is stranger than any of the three possibilities I just listed, because it turns out to have everything to do with those numbers you would have had to type in at the very beginning. We are not ready for that yet. First, we have to look at the list. The list has a definite length, and people have argued politely about that length for decades in the way physicists argue about bookkeeping. Depending on exactly how you count, whether you include the neutrino masses, whether you fold in the cosmology, whether you count a quantity or the dimensionless ratio built out of it, you get 19, or 25, or 26, or 31. The most commonly cited accounting comes from a survey published in 2006 by Max Tegmark, Anthony Aguirre, John Barrow, and Mario Livio, which put 26 dimensionless numbers in the standard model of particle physics, and 5 more in the standard model of cosmology, with a note that up to 6 further ones might be needed as observations sharpened. Nothing in tonight's argument depends on which convention you prefer. What matters is the order of magnitude of the list. It is not 3 numbers, and it is not 3,000. It is a couple of dozen, and every single one of them is a measurement rather than a result. Let me walk you through them, because seeing what is actually on the list changes how the list feels. 12 of the 26 are masses. 6 of them belong to the quarks: up, down, charm, strange, top and bottom. And 6 belong to the leptons: the electron, the muon, the tau, and the 3 neutrinos. Technically, these are entered into the theory as coupling strengths to the Higgs field rather than as masses directly, but the effect is the same. You are typing in how heavy each of the fundamental building blocks is. And when you lay those 12 masses side by side, the first thing you notice is that they make no pattern at all. The electron and the top quark are both perfectly ordinary members of the same family of particles, and the top quark is roughly 340,000 times heavier. It is heavier than an entire atom of gold, which is a genuinely absurd thing for a single elementary particle to be. The neutrinos, at the other end, are so light that we still do not know their absolute masses. We know the differences between the squares of their masses because that is what oscillation experiments measure, and we have upper limits from experiments like Katrin in Germany that weigh the tail end of tritium decay, but the actual values remain unknown. There is no formula anywhere that generates that spread. There is no principle that says the top quark should be where it is, rather than half or twice as heavy. Somebody measured it, and now it is in the theory. There is a second ratio worth putting alongside it, because it is the one that shows up in your own body. A proton is 1,836.15 times heavier than an electron. That single number decides the entire architecture of matter, because the nucleus is nearly 2,000 times heavier than the things orbiting it. The nucleus sits still, and the electrons do all the moving, and that division of labor is what chemistry is. If the ratio were closer to 1, atoms would not have a stable center and a mobile outside. They would be something else entirely, and nothing we would recognize as chemistry would happen in them. That number, 1,836.15, has also been measured to about 12 significant figures, and it has also never been derived. 3 more of the 26 are the coupling constants, which set the strengths of 3 of the 4 fundamental interactions: electromagnetism, the weak nuclear force, and the strong nuclear force. The electromagnetic one, when you express it in a form that has no units attached, no meters, no kilograms, nothing that depends on human measuring conventions, becomes the most famous unexplained number in physics. It is called the fine structure constant, and its value is approximately 1 over 137.035999177. That number governs the strength of every electromagnetic interaction in the universe. It determines the size of atoms, the colors of light that atoms emit and absorb, the chemistry that makes biology possible, and the rate at which stars fuse. It has been measured to about 11 significant figures. Its origin is completely unknown, and we will come back to what that particular number did to a couple of extremely distinguished careers. 2 more of the 26 belong to the Higgs field, the value it settles at in empty space, which is about 246 billion electron volts, and the mass of the Higgs particle itself, about 125 billion electron volts, which was measured at CERN and announced on the 4th of July, 2012. Both entered by hand. 4 more describe how quarks change from one type into another when they decay. These are the quark mixing parameters, 3 angles, and 1 additional quantity that allows the laws of physics to treat matter and antimatter slightly differently. That last one matters more than it sounds. Without that small asymmetry, there is no known route by which a universe that started with equal amounts of matter and antimatter ends up made of matter, rather than ending up made of nothing but radiation. Your existence depends on a number that we measured and cannot explain. Those mixing numbers have a pattern in them that is almost more provoking than no pattern at all. Written out as a table, they are nearly diagonal. Quarks overwhelmingly stay as the type they already are, and the off-diagonal entries, the probabilities of switching, are small but stubbornly not zero. It looks like a near symmetry that has been slightly broken by something. Nobody knows what the something is. If the table were exactly diagonal, you could argue there was a principle enforcing it. If it were random, you could argue there was nothing to explain. Instead, it is almost, but not quite, tidy, which is the most irritating result nature can hand you. 4 more do the same job for neutrinos, 3 mixing angles and a phase, describing how the 3 kinds of neutrino blend into one another as they travel. Neutrinos produced in the core of the Sun as one type arrive at the Earth partly as another, and the rate at which they do that is another set of measured inputs. And then there is the last one, which is the strangest entry on the entire list, because it is a number that appears to be 0 when nothing requires it to be. There is a parameter in the theory of the strong nuclear force, usually written with the Greek letter theta, which could in principle take any value between 0 and about 6. If it were anything much larger than 0, the neutron would have a measurable electric asymmetry, a slight separation of charge along its length, and we have looked for that asymmetry with increasing precision for over 60 years and never found it. The experimental limit puts theta below about 10 to the minus 10. That is a number sitting at 0 to 10 decimal places for no reason anyone can identify. It is called the strong charge parity problem, and it is peculiar in a way the other entries are not. The others are unexplained values, but this one is an unexplained absence. That single unexplained 0 has generated an entire industry. In 1977, a proposed solution introduced a new particle, later named the axion, whose existence would drive theta to 0 naturally. The axion has never been detected. It has, however, turned out to be one of the leading candidates for dark matter, which means several very expensive experiments are now hunting a particle that was originally invented to explain why one number on the list is smaller than it has any obligation to be. Add the cosmology, and you get about 5 more. How much dark energy there is, how much cold dark matter, how much ordinary matter, and 2 numbers describing the size and the slope of the tiny ripples in the early universe that everything else eventually grew out of. That is the list. 24 or so numbers, measured to varying precision, and the theory that uses them is silent about every one. And I want to give you the single cleanest expression of how uncomfortable this is, because it comes from the moment of discovery of one of these particles, rather than from any philosophical argument about them. When the muon was identified in the 1930s, physicists found themselves looking at what appeared to be an exact copy of the electron. Same charge, same behavior, same everything, except 207 times heavier and unstable, decaying in a couple of millionths of a second. It does no obvious job. Nothing in the universe seems to need it. The physicist Isidore Rabi, on being told about it, is supposed to have said, "Who ordered that?" That question has never been answered. Not for the muon, not for the tau, not for the mass of the electron, not for the fine structure constant, not for any of them. We have a list of the ingredients of reality, and no recipe that explains why those ingredients and not others. But notice what all of these have in common, because it is the thing that will matter in about 20 minutes. Every one of them is a fact about something, about quarks, about neutrinos, about the Higgs field, about the contents of the universe. Take the contents away, and these numbers have nothing left to be about. That is what makes the four we met at the beginning so different, and it is why they are going to take us somewhere the others cannot. But before we get there, we should spend some time with the people who tried to explain this list, because their failure is not embarrassing. It is informative. It tells you what kind of problem this is. Arthur Eddington was, by any measure, one of the most important scientists of the early 20th century. He was the man who took a photographic plate to the island of Principe in 1919 to observe a total solar eclipse, measured the deflection of starlight passing near the sun, and confirmed general relativity in front of a world that had barely heard of Einstein. He worked out the physics of how stars hold themselves up against their own weight. He wrote the first serious English-language exposition of relativity. He was, in the plainest sense, a great physicist. And he spent the last years of his life trying to prove that the fine structure constant was exactly 1/136. His argument was not empirical, it was structural, an attempt to derive the number from counting arguments about the degrees of freedom available to particles in a relativistic quantum theory. He believed, with real conviction, that a sufficiently fundamental theory would produce the constants of nature as integers, or as reciprocals of integers, the way pure mathematics produces pi. And in the 1920s, the measurements were imprecise enough that 1/136 was not obviously wrong. Then the measurements improved, and the number moved closer to 137, and Eddington produced a revised argument, one that derived exactly 137 instead. His colleagues, who were fond of him and also not blind, began referring to him as Arthur adding 1. The measurements kept improving. We now know the value to about 11 significant figures, 1/137.035999177, with an uncertainty in the last two digits. It is not 137. It is not the reciprocal of any integer. It is not, as far as anyone can tell, any simple combination of anything. Eddington's fundamental theory was published in 1946, 2 years after his death, and it stands as one of the strangest books in the physics canon, the work of a first-rate mind pursuing a program that turned out to have nothing at the end of it. That number did stranger things to Wolfgang Pauli. Pauli was one of the founders of quantum mechanics, the man who formulated the exclusion principle that keeps electrons from all falling into the lowest orbital, which is the reason matter takes up space at all. He was famously, savagely critical of sloppy thinking. His phrase for an argument so bad it could not even be evaluated, not even wrong, is still in use. And he was preoccupied with 137 for most of his adult life. He discussed it with the psychoanalyst Carl Jung. He kept returning to the question of why the universe should have chosen that particular figure. In December of 1958, Pauli was taken ill in Zurich and admitted to the Rotkreuz Hospital. According to the account that has circulated among physicists ever since, He was put in room 137, saw the number on the door, and remarked to his assistant that he would not be leaving it alive. He died there a few days later. Richard Feynman, who was not given to mysticism about anything, put the situation about as plainly as it can be put. He called the fine structure constant one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. He described it as a number that good theoretical physicists put up on their wall and worry about. Paul Dirac took a different route, and his failure is more instructive than Eddington's because it was killed by data rather than by embarrassment. In 1937, Dirac noticed that if you form certain very large dimensionless ratios out of the constants of nature, you keep getting numbers in the neighborhood of 10 to the 40th. The ratio of the electrical force to the gravitational force between a proton and an electron is about 10 to the 40th. The actual figure is close to 2.3 times 10 to the 39th, and the age of the universe, expressed in the natural time unit you can build out of atomic constants, is also about 10 to the 40th. Dirac found it intolerable that two enormous numbers arising from completely unrelated corners of physics should land in the same neighborhood by accident. So he proposed that it was not an accident, that the two are linked, and that since the age of the universe obviously increases with time, the other ratio must increase too, which means the strength of gravity must be decreasing as the universe ages. It is a beautiful idea, it is testable, and it is wrong. If the gravitational constant were weakening at the rate Dirac's hypothesis requires, the orbits of the planets would drift measurably. So people measured, laser ranging to the retroreflectors that the Apollo missions left on the Moon has now tracked the Earth-Moon distance for over 50 years to within a few centimeters, and the tracking of planetary spacecraft has done the same for the inner solar system. The current constraint on any change in the gravitational constant is smaller than about 1 part in 10 to the 13th per year. Dirac's specific proposal is excluded by many orders of magnitude. Dirac's idea did leave one lasting inheritance, though, which is the question of whether any of the constants change at all. If a constant drifted, even slightly, that would be the loose thread. It would mean the value is not a brute fact, but the current position of something dynamic, and dynamic things have explanations. So people have looked, seriously and repeatedly. In the early 2000s, a team analyzing the light from distant quasars, which passes through gas clouds on its way to us, and picks up absorption lines whose spacing depends on the fine structure constant, reported a small apparent difference between the value billions of years ago and the value now. It made headlines. Higher precision follow-ups with different instruments have not confirmed it. Meanwhile, comparisons between different species of atomic clock in laboratories now bound any present-day drift at the level of parts in 10 to the 17th per year. And there is a geological check as well. A natural nuclear reactor operated underground at Oklo, in Gabon, about 2 billion years ago, and the isotope ratios it left behind are sensitive to the fine structure constant at that time. Everything agrees. As far as anyone can measure, the number has not moved. Then came the grand unified theories, and for a while, it looked as though the whole problem might dissolve at once. The three coupling strengths of the standard model are not really constant. They change with the energy at which you probe them. In a way, the theory predicts precisely. Extrapolate them upward, and they converge toward one another. In the 1970s, it appeared that they might meet at a single point, around 10 to the 16th billion electron volts, which would mean the three forces are one force at high energy, and the three separate numbers we measure are three shadows of a single one. They very nearly meet. In the plain standard model they miss. The three lines come close, and then pass each other. And the theories that made them meet exactly, the supersymmetric extensions, predicted that protons should decay, and predicted new particles at energies the Large Hadron Collider can reach. Enormous tanks of ultra-pure water have been watched for decades for a single proton to fall apart, and none ever has. The particles have not appeared either. And then there is string theory, which was supposed to be the end of this story. The original hope, in the 1980s, was extraordinary. A theory with no free parameters at all, in which the masses and couplings would all emerge from the geometry of the extra dimensions, and every one of the 24 numbers would finally be a result rather than an input. What emerged instead was a landscape. The extra dimensions can be folded up in an enormous number of distinct configurations, each producing a different set of effective constants in the resulting universe, and the figure, usually quoted for how many, is 10 to the 500th. That is not a number with any physical comparison available. There are perhaps 10 to the 80th atoms in the observable universe, and there is no principle yet identified that picks out which of those configurations we live in. So the most ambitious attempt in history to derive the constants of nature ended not by producing them, but by multiplying the number of possible answers past any hope of counting them. I want to be careful about the tone here, because it would be easy to make this sound like a story about failure, and it is not. Every one of these people was doing exactly the right thing. Eddington was right that a sufficiently fundamental theory ought to produce the constants. Dirac was right that a coincidence between two enormous numbers demands an explanation. The grand unifiers were right that three couplings converging is a signal rather than a fluke. They were all reaching for the same thing, which is the idea that these numbers are not brute facts, but consequences of something we have not seen yet. They may still be right. Nobody has shown that the constants cannot be derived. What 100 years of this tells us is only that if there is a derivation, it is far below anything we can currently reach. And that is a useful thing to know, because it points at the second half of the problem. It is not just that we cannot explain the numbers. It is that the place where the explanation would have to live is behind a wall, and the wall, as we are about to see, is built out of 4 numbers from that same list. Go back to the hydrogen atom for a moment, because there is something in it we skipped. We said that to describe a proton and an electron, you need their charges, their masses, and the strength of the electromagnetic force between them. That is true, and it will get you most of the way. But it is not complete, and the things it leaves out are the interesting ones. The proton and the electron both have mass. Anything with mass attracts anything else with mass. So they are also pulling on each other gravitationally. And to describe that pull, you need the gravitational constant. The electron is not sitting still, and its motion involves electric and magnetic effects. So you need the 2 constants that appear in Maxwell's equations, the permittivity of free space and the permeability of free space, the electric constant and the magnetic constant. The whole system behaves quantum mechanically rather than like 2 little balls, so you need the Planck constant, which is what makes the electron occupy a smeared distribution around the nucleus rather than spiraling into it. And if you want to talk about a gas of hydrogen at some temperature rather than a single isolated atom, you need Boltzmann's constant, which converts between how hot something is and how much energy is jostling about in it. Now compare those to the list from earlier. The mass of the electron is a fact about electrons. If you removed every electron from the universe, that number would have nothing left to describe. The same is true of the top quark mass, the neutrino mixing angles, the Higgs vacuum value, all of it. These are properties of the contents. The gravitational constant is not a fact about any particular object. It is the exchange rate between energy and curvature, and it holds for a proton, a planet, a photon, or an idea of a mass that does not exist yet. Empty the universe of everything, and G is still the answer to the question of what would happen if you put something back. The speed of light is stranger still, and it is worth spending a moment on because almost everyone has the wrong picture of it. Most people first meet it as the speed photons travel, which makes it sound like a fact about light, the way the speed of sound is a fact about air. It is not. Light travels at that speed because light has no mass, and anything with no mass travels at that speed. Gravitational waves travel at it too, and they are not made of light at all. What that number actually is a conversion factor between two of the dimensions of the world you are lying in. Our universe has 4 dimensions that we know of, 3 of space and 1 of time. We measure space in meters and time in seconds, which are different units, because human beings developed the 2 habits separately and never had a reason to reconcile them. But in the geometry that actually governs how things move, time is a direction like the others, and to treat it as a direction, you need a number that converts seconds into meters. That number is the speed of light. 1 second, converted into a distance, is about 300 million meters. That is why it turns up in the mass-energy relation as well. Energy equals mass times the speed of light squared is often described as a formula about nuclear bombs, and it is really a statement about units. It says mass and energy are the same quantity measured in 2 different currencies, and it tells you the exchange rate. The reason a small amount of matter contains so much energy is not that matter is special. It is that the exchange rate is very large, because a second is a very long time compared to a meter. The Planck constant is the third of them, and it is the one that most obviously sets a scale rather than describing a substance. It has units of mass times length squared divided by time, which is the unit of a quantity physicists call action. What the Planck constant says is that action in this universe is not infinitely divisible. It comes in a smallest meaningful amount, and that amount is about 6.626 times 10 to the minus 34 in the standard units. Everything that makes quantum mechanics quantum descends from that. The reason an electron in an atom can only sit at certain energies, the reason you cannot know a particle's position and momentum with unlimited precision at the same time, the reason a laser works, the reason the transistor in the device you may be listening on works at all of it comes back to that number being small, but not 0. If the Planck constant were 0, the world would be classical, continuous, and entirely predictable, and there would be no atoms, because electrons would spiral into nuclei in a fraction of a second. That has nothing to do with electrons in particular. It is a statement about the arena. Boltzmann's constant is the 4th, and it is the humblest of them. It converts temperature into energy. It says that 1 degree of temperature corresponds to a specific quantity of jostling. It is the number that lets you take a thermometer reading, which is a human scale abstraction, and turn it into a statement about how hard molecules are hitting each other. Ludwig Boltzmann worked out the relationship between the microscopic disorder of a system and its entropy, and the equation is engraved on his gravestone in Vienna. He died in 1906, before the atomic picture he had defended for decades was universally accepted, which is one of the sadder pieces of arithmetic in the history of science. So there are 4 of them: gravity, geometry, granularity, and heat. 4 numbers that are not facts about the furniture, but facts about the room. And there is a detail about these 4 that has changed very recently, and that will matter later tonight, so I want to plant it now while it is easy. 3 of those 4 are no longer measured. They are defined. On the 20th of May, 2019, the International System of Units was rebuilt from the ground up. The speed of light had already been fixed by definition since 1983. The meter stopped being a thing and became the distance light travels in a specified fraction of a second. In 2019, the Planck constant and Boltzmann's constant joined it. The Planck constant is now exactly 6.6260715 times 10 to the minus 34 joule seconds, with no uncertainty at all, because that is now what defines the kilogram. Boltzmann's constant is exactly 1.380649 times 10 to the minus 23 joules per Kelvin, because that is now what defines the degree. The change retired the last physical object in the entire system of measurement. Until that day, the kilogram was a cylinder of platinum and iridium sitting in a vault outside Paris, and everything anyone had ever weighed was, ultimately, compared to that cylinder. It had been quietly losing mass relative to its own official copies for a century, which meant that by definition, the kilogram was drifting, and nobody could say in which direction. Now it is defined by a number instead of an object, and Planck's ambition from 1899, units that do not depend on any artifact, any planet, any civilization, is close to fully realized. But only 3 of the 4 made it. The gravitational constant is still measured, and it is measured badly. Its value is 6.67430 times 10 to the minus 11 in the standard units, with an uncertainty of about 22 parts per million. That sounds precise until you compare it to its neighbors. The fine structure constant is known about 100 million times better. We have been measuring the gravitational constant since Henry Cavendish hung 2 lead spheres from a torsion wire in 1798, and after more than 220 years, we know it to 5 or 6 significant figures, while some atomic quantities are known to 12. Worse, the most careful modern measurements disagree with one another by more than their own stated error bars, which in experimental physics is the standard signature of a systematic effect that nobody has found yet. Gravity is difficult to measure because you cannot shield it, cannot switch it off, and cannot make a laboratory source heavy enough to drown out the rest of the planet. So the weakest of the 4 forces is also the one we know least accurately, and that turns out to be more than an inconvenience. And there is a beautiful piece of history in the middle of this that shows how much can fall out of constants like these when you simply look at them carefully. In the 1860s, James Clerk Maxwell was working on the equations that unified electricity and magnetism. 2 constants appear in those equations: the electric constant, which governs how strongly charges push and pull through empty space, and the magnetic constant, which governs the corresponding magnetic effects. Both of them had been measured in laboratories using nothing more exotic than coils, batteries, and capacitors. Neither had anything to do with light. Maxwell noticed that if you combine them in a particular way, 1 divided by the square root of their product, you get a quantity with the units of a speed. So he worked out what speed, and the answer came out at approximately 310,000 kilometers per second, which was, within the experimental error of the day, the measured speed of light. He had not gone looking for light. He had 2 numbers from benchtop electrical experiments and a piece of dimensional arithmetic, and out of them came the speed of a beam crossing a room. Maxwell drew the obvious conclusion, which was that light is an electromagnetic wave, one of the great unifications in the history of physics, and it arrived through the back door by manipulating constants. Hold on to that, because we are about to do exactly the same trick, with different constants, and it is going to take us somewhere considerably less comfortable. Take g, take the speed of light, take the Planck constant, 3 numbers that describe the arena rather than the contents. Combine them and see what comes out. Somebody did that, and he did it in 1899, before there was any such thing as quantum mechanics. Max Planck was 41 years old in the spring of 1899, and he was in the middle of a long, unglamorous piece of work that had been going on for 2 years and was not going especially well. The problem he was attacking was the radiation given off by hot objects, the reason a poker in a fire glows red and then orange and then white as it heats. There was an experimental curve, measured carefully by colleagues in Berlin, that described exactly how much light of each color a perfectly absorbing object emits at a given temperature. And there was no theory that produced that curve. Classical physics predicted something that went wrong at the short wavelength end in a manner so severe it was eventually nicknamed the ultraviolet catastrophe. Planck had been publishing his attempts in installments under the title On Irreversible Radiation Processes. The fifth and final installment was presented to the Prussian Academy of Sciences in Berlin in May of 1899 and printed in the Proceedings, Volume 5, pages 440 to 480. It is a 40-page paper about thermodynamics and radiation, and at the very end of it, occupying the last 3 pages, there is a short section that has almost nothing to do with the rest, headed Natural Units of Measure. It is close to an afterthought. It reads like a man clearing his throat about something that had been bothering him. What was bothering him was this: every unit human beings use is an accident of human history. The meter was defined in the 1790s as 1/10,000,000th of the distance from the North Pole to the equator, along a meridian through Paris, and even that was measured slightly wrong. The second descends from Babylonian arithmetic: 60 seconds, 60 minutes, 24 hours, none of which has any physical significance whatsoever. The kilogram, at that point, was a lump of metal in a French vault. Every measurement in every laboratory on Earth was ultimately expressed in terms of the size of one planet and the counting habits of one ancient civilization. Planck wanted units that were not like that, and he realized that the constants appearing in his own radiation work gave him a way to build them. Here is the moment, as best as it can be reconstructed. It is May, in Berlin, in the last year of the 19th century. The lecture room of the Prussian Academy is full of men in dark coats, listening to the 5th installment of a paper on a problem most of them consider technical rather than fundamental. Planck reaches the final section. He has 3 quantities in front of him: the gravitational constant, which has been known in some form since Newton, the speed of light, measured to reasonable precision by that point, and a new constant, arising out of his own work on the entropy of oscillating charges, which he calls B. The letter H, and the name it will eventually carry, are still in the future. He points out that these 3 quantities have units, and that the units can be combined so as to cancel. He writes down a length, he writes down a mass, and a time, and a temperature. And then he says the thing that makes this moment worth stopping on, which is that these units, and he means it literally, necessarily retain their meaning for all times and for all civilizations, even extraterrestrial and non-human ones. He is saying, in a room in Berlin in 1899, that if there is anybody else out there doing physics, they will arrive at these same 4 numbers, because the numbers do not come from us. Then he finishes his talk, and the paper goes into the proceedings, and almost nobody pays any attention to the last 3 pages for 50 years. It is worth pausing on how radical that sentence actually was for its moment. In 1899, nobody had any evidence that other civilizations existed, and the question was not respectable science. Planck was not speculating about them. He was using them as a test, a way of asking whether a quantity is a fact about nature or a fact about us. If a measurement would mean something to a physicist who had never seen the Earth, never counted in 60s, never heard of Paris, then it is real. If it would not, then it is bookkeeping. It is the same instinct that would later be used to design the plaques bolted to the outsides of spacecraft, which describe distances in terms of the hydrogen atom rather than in meters, for exactly the same reason. Planck applied that test to the constants he had in front of him, and 4 numbers passed it. Now hold the date in your mind, because the chronology is the strange part. In May of 1899, there was no quantum mechanics. Planck's own quantum hypothesis, the suggestion that energy is exchanged in discrete packets, was 19 months away, and when he did introduce it, in December of 1900, he regarded it as an act of desperation, a mathematical trick to make the equation fit, not a statement about how nature works. He spent years afterwards trying to get rid of it. There was no special relativity. That arrives in 1905. There was no general relativity, no curved space-time, no notion that gravity has anything to do with geometry. That arrives in 1915. There was no quantum field theory, no atomic nucleus. The nucleus is discovered in 1911. No notion of a fundamental particle in the modern sense, and absolutely no reason for anybody to suppose that a length of 10 to the minus 35 meters had any physical meaning at all. And yet the four numbers Planck wrote down on those last 3 pages are, we now believe, the exact scale at which 20th century physics stops working. He was not predicting that. He could not have been. He had no theory that broke down anywhere, because he had barely half of the theories involved. He was doing housekeeping, trying to get the arbitrary human accidents out of the system of measurement, and the housekeeping produced the boundary of the subject. For most of the next 50 years, this was treated as a curiosity. The numbers were regarded as numerology, interesting arithmetic, with no evident physical content, the sort of thing you mention in a footnote. It was only when people began seriously trying to combine quantum mechanics with general relativity, from roughly the 1930s onward, and found that every such attempt fell apart at a particular scale, that anyone noticed the scale was already written down, in the back of a paper about hot objects, from the year before the quantum was invented. There is a small irony buried in the neglect, too. The constant Planck called B, the one that made the whole construction possible, was itself something he did not believe in for years. It came out of his radiation formula as a fitting parameter, a quantity that had to be there for the curve to match the data, and he spent the following decade trying to find a way to derive his results without it. He was not a revolutionary by temperament. He was a careful, conservative thermodynamicist who found himself holding the first piece of quantum mechanics and did not want it. The constant that anchors the entire scale we are discussing tonight entered physics as an unwelcome guest. That is the first genuinely uncomfortable thing in this story. The boundary of our understanding was not discovered by running into it. It was calculated, from 3 constants, by somebody who had no idea what he was calculating. We still have not answered the question we started with, but we now have the tool that produces it, so let us actually do the arithmetic. The method Planck used is called dimensional analysis, and it is the sort of thing that gets taught in a first-year physics course and then quietly does more work over a career than most of the fancier tools. The idea is that every physical quantity carries units, and units follow rules. A speed is a length divided by a time. An energy is a mass times a length squared divided by a time squared. You cannot add a speed to an energy any more than you can add 3 meters to 4 kilograms. The sentence does not pass. And because units follow rules, you can often work out the form of an answer before you know any of the physics, simply by asking what combination of the available quantities has the right units. So look at the 3 constants we have. The gravitational constant has units of length cubed divided by mass divided by time squared. The Planck constant, the reduced version, h divided by 2 pi, which is the one that actually appears in the quantum equations, has units of mass times length squared divided by time. The speed of light has units of length divided by time. Between them, those 3 cover 4 independent things. Length, mass, and time appear across them in different combinations, which means that if you ask what combination of these 3 quantities produces something whose units are pure length, with no mass and no time left over, the question has an answer, and, crucially, it has only one answer. The answer is the square root of the gravitational constant times the reduced Planck constant, divided by the speed of light cubed. That is not a choice. There is no other way to arrange those 3 constants that leaves you holding a length. You could multiply the result by 2 or by pi, or by the square root of 8 pi, and different authors do exactly that. Those factors of order 1 are convention. But the scale is fixed. Any physicist anywhere in the universe, given those 3 numbers and asked for a length, gets the same answer to within a factor of a few. Put the measured values in, and it comes out as 1.616255 times 10 to the minus 35 meters. That is the Planck length. In the most recent International Adjustment of the Constants, published in 2022, its uncertainty is about 1 part in 100,000, and all of that uncertainty comes from the gravitational constant, because the other 2 are now exact by definition. Ask the same question for a time instead of a length, and you get the square root of the gravitational constant times the reduced Planck constant divided by the speed of light to the 5th power, which is the same thing as the Planck length divided by the speed of light, the time it takes light to cross 1 Planck length. That comes out at 5.391247 times 10 to the minus 44 seconds. The Planck time. Ask for a mass, and you get the square root of the reduced Planck constant times the speed of light divided by the gravitational constant, 2.176434 times 10 to the minus 8 kilograms. Multiply that mass by the speed of light squared, and you have the Planck energy, about 1.956 times 10 to the 9th joules, or equivalently, about 1.22 times 10 to the 19th billion electron volts, which is the unit particle physicists actually use. And if you bring in the 4th constant, Boltzmann's, and divide the Planck energy by it, you get a temperature, 1.416784 times 10 to the 32nd Kelvin, the Planck temperature. There are others. There is a Planck area, which is the Planck length squared, about 2.6 times 10 to the minus 70 square meters, a quantity that turns up in the formula for the entropy of a black hole, and which is, oddly, one of the very few places the Planck length appears in a result that most physicists think is actually correct. There is a Planck density, 1 Planck mass in 1 Planck volume, which comes out at about 5 times 10 to the 96th kilograms per cubic meter, against water at 1000. There is a Planck momentum, and a Planck power, and a Planck charge. The Planck area is worth 1 extra sentence, because of where it shows up. In the 1970s, Jacob Bekenstein and Stephen Hawking worked out that a black hole has an entropy, and that the entropy is proportional to the area of its horizon rather than to its volume, which was already surprising. When you write that result out properly, the entropy comes out as 1/4 of the horizon area measured in Planck areas. In other words, the natural currency in which the information content of a black hole is counted is the Planck area, as though the horizon were tiled in patches of that size, each one carrying about 1 bit. That result is not a speculation on the fringe of the subject. It is one of the few things about quantum gravity that nearly everyone working on the problem believes is correct, and the Planck length is sitting right in the middle of it. But the 4 Planck wrote down in 1899, length, mass, time, temperature, are the ones that matter, because those 4 are exactly the 4 independent dimensions you need to build a complete system of measurement, which is precisely why 4 constants were enough. Once you have a length, a mass, a time, and a temperature, you can express any physical quantity in the universe without ever mentioning a meter, a kilogram, a second, or a degree. Working physicists do this constantly, and it is worth knowing because it removes some of the mystique. In a great deal of theoretical work, people simply set the speed of light, the reduced Planck constant, and sometimes the gravitational constant, equal to 1, not approximately 1, exactly 1, by choice of units. Every factor of c disappears from the equations. Energy and mass become the same symbol. Time and distance become the same symbol. It does not change any physics. You can restore the constants at the end by dimensional analysis whenever you need a number, but it strips the human measuring conventions out of the algebra entirely, and what is left is the structure. That is what people mean when they call these the universe's own units, and the phrase is fair up to a point. It is fair in the sense Planck intended. These are the units you would arrive at without any reference to Earth. It is not fair if it is taken to mean that the universe somehow counts in them, or that there is a smallest tick and a smallest step, and reality advances one Planck length at a time, like frames in a film. That claim is very common, and it is not established, and we are going to take it apart properly in a while. One more caution before we move on, and it is about those factors of order 1. A fair number of theorists prefer what are called reduced Planck units, which are built using 8 pi times the gravitational constant instead of the gravitational constant on its own, because that combination is what actually appears in Einstein's field equations. Using them shifts every Planck quantity by a factor of about 5. That is not a disagreement about physics. It is a disagreement about where to put a constant. But it is a useful reminder that when somebody tells you the smallest possible length is 1.6 times 10 to the minus 35 meters, the 1.6 is a convention, and the 10 to the minus 35 is the physics. The scale is real. The decimal places are furniture. So let us sit with what we have actually just done, because it is a strange piece of work when you look at it directly. We took 3 numbers that describe the arena rather than its contents. 3 numbers that nobody can derive, that have no explanation, that simply have to be measured and typed in. We did nothing with them except cancel their units against each other. Arithmetic a school student could follow. And out fell a length, a time, a mass, and a temperature. No experiment produced these. No theory of anything was consulted. There is no observation of a Planck length anywhere in the scientific record, and there never will be, for reasons we will get to. The numbers exist because the algebra had nowhere else to go. And when physicists eventually built theories that could be pushed to that scale, quantum field theory on one side, general relativity on the other, they found that both of them, independently, fall apart there. Try to calculate a gravitational interaction between 2 particles at Planck scale energies using the standard toolkit, and the answer is not a large number. It is infinite, and unlike the infinities in other quantum field theories, this one cannot be tidied away. The method that saved quantum electrodynamics does not work on gravity. So the scale that came out of pure unit arithmetic in 1899 turned out to be the scale where our understanding runs out. That coincidence is either the most important clue in physics, or an accident so large that calling it an accident feels like a category error. We still are not ready to say which, but we can now look at the length itself, and it deserves a proper look. Let us step back for a moment and put the pieces on the table together, because we have covered a fair amount of ground, and the next stretch goes further down. We started with a list of about 24 numbers that have to be measured and typed into physics by hand, with no derivation, no pattern, and no explanation after a century of very serious attempts. We notice that almost all of them are facts about objects, masses of particles, strengths of interactions between particular things. We separated out 4 that are not: gravity's constant, the speed of light, the Planck constant, and Boltzmann's constant, which describe the arena rather than its contents. We watched Maxwell take 2 benchtop electrical constants and get the speed of light out of them by pure unit arithmetic. And then we watched Planck, in the last 3 pages of a paper about hot objects, do the same trick with 3 arena constants and produce a length, a time, a mass, and a temperature, 26 years before quantum mechanics was finished, and 16 years before general relativity existed. That is where we are. Now the length. 1.616 times 10 to the minus 35 meters is a number that does not respond to the usual tricks for making small things comprehensible, because every comparison you might reach for is itself unimaginably larger. Start with something small that you have at least heard of. An atom is roughly a tenth of a nanometer across, 10 to the minus 10 meters. The nucleus at its center is about 10 to the minus 14 meters, which means that if you scaled an atom up to the size of a football stadium, the nucleus would be a grain of rice on the center spot, and the rest would be empty. A proton inside that nucleus is around 10 to the minus 15 meters. The Planck length is 20 orders of magnitude below the proton. 20 orders of magnitude is a factor of 100 billion billion. And the trouble with saying that is that the phrase slides straight off the mind, so let me try it a different way. Take a proton. Now expand it, uniformly, until it is the size of the entire observable universe. All 93 billion light-years of it. Every galaxy we can see. The whole of it. Under that same magnification, the Planck length would be about the width of a grain of sand. That is the gap between the smallest object we have ever actually studied and the smallest length we can even discuss. There is more room than there is between a grain of sand and everything. I want to take you down through it, slowly, because the emptiness on the way is the point. Hold your hand in front of you. You are at about a tenth of a meter. Go down by a factor of 1,000, and you are at a tenth of a millimeter, the width of a human hair, the smallest thing your eye can resolve unaided. Another 1,000, and you are at a tenth of a micron, well inside a living cell, among structures that would fill a textbook. Another 1,000, and you are at the size of a small molecule. Another, and you are inside the atom, and the outer electrons are somewhere behind you. Another factor of 10,000, and you reach the nucleus, and then the proton, and inside the proton there are quarks, and a violent field of gluons holding them, and this is the deepest layer we have ever confirmed. Everything humanity has ever detected, every particle in every experiment ever run, is at or above this level. And now keep going. Another factor of 1,000, and there is nothing. Another 1,000, nothing. Another, and another, and another. 20 orders of magnitude of falling with no known object of any kind in any of it. No structure, no landmark, nothing at all that physics has ever seen. And then, at the bottom of that long empty drop, the arithmetic hands you a number, and the number is where the equations stop making sense. That is the Planck length. Nothing found on the way down, nothing observed at the end, a destination produced entirely by cancelling units. If you took that same journey in the other direction, starting at the Planck length and climbing back up by factors of 1,000, you would pass through 20 steps of complete silence before you arrived at the first thing anybody has ever measured. It is the longest stretch of unexplored territory in the physical sciences, and it sits underneath everything you have ever touched. It is worth turning that around and looking at it from the other end, because the symmetry is remarkable. The observable universe is about 8.8 times 10 to the 26th meters across. The Planck length is about 10 to the minus 35 meters. Between the largest thing we can point at and the smallest thing we can name, there are roughly 62 orders of magnitude, and that span contains every scale that physics has anything to say about. Every galaxy, every star, every organism, every atom, every quark. 62 powers of 10 is the whole of it. And you, standing in the middle of that, are at about 1 meter, which puts a human being not quite at the geometric center of the range, but startlingly close to it. We are, in the scale of things, closer to the midpoint between the universe and the Planck length than to either end. That is probably not meaningful. It is very hard not to notice. The other thing about that long fall through 20 empty orders of magnitude is that physicists have a name for it, and the name tells you how uncomfortable it makes them. They call it the desert. The expectation, in the standard picture, is that between the energies we can reach in accelerators and the Planck energy, There is essentially nothing. No new particles, no new forces, no new structure. Just the same physics running unchanged across 15 orders of magnitude. Nature has not previously behaved that way. Every time we have opened up a new range of scales, from the atom to the nucleus to the quark, we have found something living there. A desert that large would be unprecedented, and a good many theorists find it implausible enough that most proposed extensions of the Standard Model exist mainly to put something into it. So far, nothing has been found in it. Now here is the crucial correction, and it is the single most commonly repeated wrong thing about this subject, so I want to be careful. You will very often hear that the Planck length is the pixel size of the universe, the smallest possible distance, the point at which space stops being continuous and becomes a grid, like the resolution limit of a screen. It is a satisfying picture, and it is not what anyone has established. What has been established is narrower and, I think, considerably stranger. The Planck length is the scale at which our two working theories can no longer both be used. It is also, and this is a separate result with an independent argument behind it, the scale at which the operation of measuring a distance stops functioning, for a reason we will go through properly in a while. Neither of those statements says that nothing smaller exists. In fact, physics contains an obvious counterexample. According to general relativity, taken at face value, the center of a black hole is a singularity, a point of zero size and infinite density. Zero is very much smaller than 10 to the minus 35. Almost no physicist believes that description is literally true. It is generally taken as a sign that the theory has been pushed past its limit. But the theory itself does not contain a rule forbidding sub-Planckian distances. Nothing in general relativity says space is grainy. Nothing in quantum mechanics says it either. So the honest statement is this: below the Planck length, we do not know what there is, and we do not currently have a way to find out. It might be a smooth continuum going down forever. It might be granular. It might be something that is neither, and that the words smaller and distance simply stop applying to. Anyone who tells you flatly that it is the smallest possible length is telling you a conclusion that is not in evidence. There is one more thing worth noticing about the number itself, and it is the sort of detail that changes how the whole subject feels. We know where the boundary of physics is, to about 1 part in 100,000. That is a very precise statement about a place nobody has ever been. The uncertainty in the Planck length comes entirely from the gravitational constant, because the other two ingredients are now defined exactly, and gravity is the worst measured constant we have. If somebody tomorrow measured the gravitational constant 100 times more precisely, the location of the edge of our understanding would move slightly, and we would know it 100 times better. Think about what an odd situation that is. We can specify the boundary of the knowable to 5 decimal places. We can compute its area, its associated energy, the temperature that goes with it. We can carry it around in equations and use it as a unit. And we cannot say one single thing about what is on the other side of it, or why it is there rather than somewhere else, because the constants that place it are constants nobody has ever explained. Which brings us to the second of Planck's 4 numbers, and to a question that turns out to be harder than how small. The Planck time is the Planck length divided by the speed of light. It is, quite simply, how long light takes to cross the smallest distance we can talk about. It comes out at 5.39124, 7 times 10 to the minus 44 seconds. I am not going to try to make that number feel small by comparison, because the comparisons fail the same way they failed for the length. The shortest intervals human beings have ever measured directly are attosecond pulses used to watch electrons move inside atoms, and an attosecond is 10 to the minus 18 seconds. The Planck time is 26 orders of magnitude below that. If you counted Planck times at 1 per second, You would need far longer than the age of the universe to count out a single tick of a wristwatch. But the number is not the interesting part. What matters is where it sits in the story of the universe, because the Planck time has a job that the Planck length does not. The universe, according to the standard cosmological picture, is about 13.8 billion years old. Run the expansion backwards, and everything gets hotter and denser, and the theory holds up remarkably well for an astonishing distance backwards. We can describe the formation of the first atoms, the forging of the first light nuclei, the moment the strong force confined quarks into protons. Keep going back, and the confidence drops, but the physics still functions in outline. Go back to about 10 to the minus 32 seconds, and you are in the era where inflation is supposed to have happened, which is speculative, but at least describable. And then you reach 5.4 times 10 to the minus 44 seconds after the beginning, and everything stops. Not because the data runs out, because the description does. At that moment, the energy density of the universe reaches the Planck density, roughly 5 times 10 to the 96th kilograms per cubic meter. And every theory we have of how matter and space-time behave requires both quantum mechanics and gravity simultaneously, which is precisely the combination that produces infinity instead of an answer. This is what people mean when they refer to the Planck era. It is not a period we understand poorly. It is a period we cannot currently write down at all. The equations do not give bad answers there. They give no answers. Every quantity you try to compute diverges. It is also, in the standard picture, around the moment when the four fundamental forces would have been a single thing: gravity, electromagnetism, the weak and the strong. At ordinary energies, they are four separate interactions with four separate strengths, but their strengths change as energy rises, and the expectation is that at sufficiently high energy, they converge into one. The Planck scale is where gravity would finally join the other three. So the first moment we cannot describe is also, plausibly, the last moment when physics was simple, when there was one force instead of four, and one number instead of 24. We have no model of it. We have a name for it, and the name marks the place where the models expire. Put yourself there for a moment, as far as the idea allows. The universe is 5.4 times 10 to the minus 44 seconds old. There is no space in the sense you are used to. Nothing you could lay a ruler across. Nothing that stays still long enough to be measured. There is no separation yet between the force that holds a nucleus together and the force that holds you to the floor. Whatever they are one thing. The temperature, if temperature still means anything here, is around 1.4 times 10 to the 32nd degrees, which is roughly 10,000 trillion times hotter than the center of the sun. Everything that will ever exist is present, and none of it has any of the properties it will later have. And you turn, as anyone would, and you look one step earlier, and the instruction does not fail, because the light is too faint or the instrument too crude. It fails because there is no earlier for the sentence to point at. There is one piece of arithmetic here that is worth doing simply because of how it lands. Divide the age of the universe by the Planck time, and you get roughly 8 times 10 to the 60th. That is the number of Planck ticks that have elapsed since the beginning, if such a count means anything at all. And whether it means anything is exactly the open question. Under one reading of the Planck scale, it is a real count of real steps, like frames of a film. Under another, it is a purely formal number, with no more physical content than dividing the age of the universe by the length of a piece of string. Now here is the part I want you to actually sit with, because it is not the same as ordinary ignorance, and it took me a long time to appreciate the difference. The obvious question is, what happened before that? And the honest answer is not, we don't know. The honest answer is that the question may not be a question. Time, in general relativity, is not a stage that events happen on. It is part of the structure of space-time, and space-time is something the theory describes as a physical, dynamical thing. It bends, it stretches, it responds to what is in it. If space-time itself becomes indefinite at the Planck scale, then so does time, and a moment that comes before, the first moment that any theory can describe, is not a moment sitting just out of reach, waiting for better equipment. It may be a phrase with nothing behind it. Stephen Hawking had an analogy for this that has never been improved on. Asking what came before the beginning of time, he said, is like asking what is north of the North Pole. That is not a difficult question. It is not an unanswered question. It is a question whose grammar fails. You can stand at the North Pole and point in any direction you like, and every direction you point is south. There is no hidden extra territory that better navigation would reveal. The concept simply runs out, and it runs out because north was always defined relative to a structure that ends there. And that is a fundamentally different species of not knowing from the kind we are used to. Most of what science does not know is the ordinary kind. We do not know what dark matter is made of, but the question is perfectly well posed, and someone may answer it in your lifetime. We do not know whether there is life elsewhere, but that is a question about a fact, and the fact is either true or false. Those are gaps in the map. What sits at the Planck scale is not a gap in the map. It is the place where the map stops being a map. The words we use to ask the question, before, smaller, when, where, are all things that the theory produces rather than assumes, and asking to use them outside the range where the theory works is like asking what a photograph looked like before the film was invented. That is worth a moment, because almost everyone carries an unexamined assumption in the opposite direction. From childhood, most of us picture time as a road running backwards forever. Something happened, and before it something else happened, and before that something else, and the only obstacle to seeing further back is how good our instruments are. It feels like a fact about the world. It is really a fact about how we think. At 5.4 times 10 to the minus 44 seconds, the road may simply stop being a road, not blocked, not hidden, just not extending in that direction, because the direction is one of the things the road was made of. We do not know that this is the case, and I want to be careful about the difference between saying, this might be true, and this is true. Some approaches to quantum gravity do produce a before, bouncing cosmologies in which our expansion follows a previous contraction, and the moment we call the beginning is a transition rather than an origin. Those are real, serious models. They are also entirely untested. What we can say with confidence is that the first tick of the clock we can describe is at 5.4 times 10 to the minus 44 seconds, that it is placed there by three constants nobody can explain, and that everything before it is either unknown or not a coherent thing to ask about, and at the moment we cannot even tell which of those two it is. And now for the strangest number in the whole set. Because so far everything has been at an extreme, a length too small to picture, a time too short to name. The next one is a flea's egg. Every Planck quantity we have looked at so far has been at an extreme so severe that no comparison survives contact with it. A length 20 orders of magnitude below a proton, a time 26 orders of magnitude below the shortest interval ever measured, a temperature of 100 million degrees, a density of 5 times 10 to the 96th kilograms per cubic meter. And then there is the Planck mass, 2.176434 times 10 to the minus 8 kilograms, which is 21.76 micrograms. That is a flea's egg. It is roughly a millionth of the mass of a housefly. It is a few thousandths of a grain of table salt. It is a quantity you could, with a good enough laboratory balance, actually weigh, not indirectly, not by inference, but by putting it on a scale. Sitting at the bottom of physics, among numbers that defeat every attempt at comparison, is one number that is a speck of dust. It is a weight you could not feel. If somebody placed one Planck mass on your open palm, you would not notice it had arrived, and you would not notice when it left. The mass is not the only one that behaves this way either. There is a Planck momentum as well, and it comes out at about 6.5 kilogram-meters per second, which is roughly the momentum of a cricket ball thrown moderately hard, or a house brick moving at walking pace. Again, a quantity from the deepest level of physics that turns out to be something a person could produce with their arm. Two of Planck's quantities are on human scale, and they are the two that involve mass, which is not a coincidence and is about to become the whole story. And I want to be clear that this is not a coincidence or a quirk of the units. It is the single most important fact in this entire subject, and it is the reason the Planck scale is a wall rather than merely a curiosity. Start by comparing it to the things the Standard Model actually contains. A proton has a mass of about 1.67 times 10 to the minus 27 kilograms. The Planck mass is about 10 to the 19th times heavier than a proton, 10 billion protons, in a single fundamental unit. If elementary particles came in Planck masses, a single one of them would weigh as much as a small bacterium, and a handful of them would be visible. They do not, of course. Every particle we know of is fantastically lighter than this. The heaviest thing in the Standard Model, the top quark, is about 10 to the 17th times lighter than the Planck mass. So we have a very sharp question. Why is the natural mass scale of the universe, the one that falls out of gravity, the quantum, and geometry, 19 orders of magnitude above everything the universe is actually made of? The answer is one sentence long, and it is a sentence about gravity. Gravity is unbelievably weak. Everyone knows this in some form. You have known it since you were a small child, without ever putting it that way. Pick up a paperclip with a fridge magnet, and a piece of magnetized metal the size of a coin defeats the gravitational pull of an entire planet, 6 times 10 to the 24th kilograms of rock, all pulling downward, and the coin wins. Every time you stand up, you overcome the gravitational attraction of the whole Earth using chemical energy from a sandwich. But the numbers are worse than the intuition suggests. Take 2 protons and sit them next to each other. Compute the electrostatic repulsion between them. They are both positive, so they push apart. Then compute their gravitational attraction. The ratio of gravity to electromagnetism comes out at about 8 times 10 to the minus 37. Gravity, between those 2 protons, is about 1,000 trillion times weaker than electromagnetism. For 2 electrons it is worse still, about 10 to the minus 43. Gravity between 2 electrons is 10 million trillion times weaker than the electrical force between them. This is why gravity plays no role whatsoever in chemistry, in nuclear physics, in particle physics, in anything at all at small scales. It is not a small correction that we neglect for convenience. It is so far below every other effect that in most of physics it does not appear at all. And now the connection, which is the piece most accounts leave out. The Planck mass is defined as the mass at which gravity stops being negligible. It is the point where the gravitational interaction between 2 objects becomes comparable in strength to the other interactions, where gravity finally has to be taken seriously at the quantum level. And because gravity is weaker than electromagnetism by a factor of around 10 to the 36, you have to pile up an enormous amount of mass before the gravitational effect catches up. So the Planck mass is large because gravity is weak. Those are the same fact, viewed from 2 sides. If gravity were stronger, the Planck mass would be smaller, the Planck length would be larger, and the boundary of physics would sit somewhere we could reach. The reason the edge of our understanding is so far away is precisely that the force which defines it barely does anything. Let me put the energy in terms you can hold. because this is where it becomes genuinely peculiar. Take that flea's egg of a mass and convert it to energy using the mass-energy relation. Multiply 21.76 micrograms by the speed of light squared, and you get about 1.96 billion joules. For comparison, a full 50-litre tank of petrol in a car contains around 1.7 billion joules of chemical energy. The Planck energy is, to within about 15%, the energy in a tank of fuel. Of all the ways the universe could have chosen to hide its most inaccessible scale, it chose to make the energy something you have handled, unthinkingly, hundreds of times. That is the number the entire subject is organized around. Not an unimaginable quantity. Not the output of a star, the amount of energy you buy at a filling station on a Tuesday morning and think nothing of. The catch, and it is the whole catch, is where you have to put it. Particle physicists do not measure energy in tanks of petrol. They measure it in electron volts, and the Planck energy expressed that way is about 1.22 times 10 to the 19th billion electron volts. The Large Hadron Collider, the most powerful accelerator ever built, collides protons at 13.6 trillion electron volts. The gap between those two numbers is a factor of roughly 900 trillion. That is not a gap you close with a bigger budget. To reach Planck energy, with current accelerator technology, you would need a machine with a circumference of something in the region of a light year. There is no engineering path, no clever technique, no incremental improvement that closes 15 orders of magnitude. The most optimistic projections for accelerators over the next century move the number by a factor of 10 or so, which against 10 to the 15 is not movement at all. So the energy is ordinary. The concentration is not. What the Planck scale asks for is the contents of a fuel tank compressed into a volume 10 to the minus 35 meters across, and there is no process in the universe, natural or artificial, that we know how to arrange. This mismatch between the scale at which everything actually is and the scale where gravity would matter has a name in particle physics, and it is one of the most important open problems in the field. It is called the hierarchy problem. Why is the mass scale of the Higgs field, around 246 billion electron volts, 16 or 17 orders of magnitude below the Planck scale? In a quantum theory, the calculated corrections to the Higgs mass should naturally drag it up toward the highest scale in the problem, which is the Planck scale, and something appears to be holding it down with extraordinary precision. For 40 years, the leading proposed answer was supersymmetry, a theory in which every known particle has a heavier partner whose contributions cancel the ones pushing the Higgs mass up. It was elegant. It explained the hierarchy. It fixed the convergence of the coupling constants, and it supplied a dark matter candidate. It made one requirement: the partner particles had to be light enough for the Large Hadron Collider to find. The collider has now looked, thoroughly, for well over a decade. Nothing has appeared. The exclusion limits have climbed steadily through the mass ranges where the simplest and most attractive versions of the theory lived, and those versions are now gone. More elaborate variants survive, but they survive by giving up the thing that made the idea appealing in the first place, which was that it explained the hierarchy without any tuning at all. So we are left with the flea's egg and the ordinary tank of petrol and a wall we cannot reach. And you might reasonably think that the barrier is simply engineering, that in principle, with an absurd enough machine, you could get there. You could not. And the reason why is the most elegant piece of the entire argument. To see a small thing, you have to hit it with something smaller. That is the whole principle of every microscope ever built, and it has been understood since the 1870s, when Ernst Abbe worked out that an optical microscope cannot resolve detail much finer than about half the wavelength of the light you are using. Green light has a wavelength of around 500 nanometers, so you cannot see structures much below 200 nanometers, no matter how good the lenses are. It is not a manufacturing problem. The wave you are looking with is simply too coarse to register the feature. The way around it is to use a shorter wave. X-rays have wavelengths comparable to the spacing between atoms in a crystal, which is why X-ray crystallography can map molecular structure. Electrons, which behave as waves with a wavelength that shrinks as their energy rises, do better still, which is why electron microscopes can image individual atoms. That electrons have a wavelength at all is worth a sentence of its own, because it is one of the more beautiful accidents in this chain. In 1924, Louis de Broglie proposed in his doctoral thesis that if light could behave as a particle, then particles ought to behave as waves, with a wavelength inversely proportional to their momentum. It was a startling suggestion from a graduate student, and his examiners were unsure what to do with it. 3 years later, Clinton Davison and Lester Germer fired electrons at a nickel crystal and got a diffraction pattern, the unmistakable signature of a wave. The idea was correct, and the practical consequence is that every particle in the universe is a potential microscope, with a resolution set entirely by how hard you can push it. And that gives you the general rule, which is the rule that governs everything from here on. To resolve a distance, you need a probe whose wavelength is comparable to that distance. Shorter wavelength means higher energy, so every step down in scale costs energy, and the cost rises as the scale falls. This is exactly what particle accelerators are. They are not primarily machines for making new particles. They are microscopes with terrible ergonomics. Scattering experiments at Stanford in the late 1960s fired high-energy electrons at protons and, from the way they bounced, revealed that the proton has structure inside it, the discovery of quarks, which won the Nobel Prize in 1990. The Large Hadron Collider works on the same principle at far higher energy, which is why it can probe distances around 10 to the minus 19 meters. So the recipe seems clear. Want to see the Planck length? Build a bigger microscope. Turn the energy up. Let us do that, in imagination, with no budget and no engineering constraints, and see what happens. You are commissioning the machine. It is a ring, and you can make it as large as you like, around the Earth, around the solar system, whatever the physics requires. You start at the energies we already have. The image sharpens. You resolve structures at 10 to the minus 19 meters, and then, as you push the energy higher, 10 to the minus 20, 10 to the minus 22, everything is behaving. Every increment of energy buys you a proportional increment of resolution, exactly as the rule promises. You keep going. 10 to the minus 25, 10 to the minus 30. And then the returns begin to change. Because there is a second thing that energy does, and up to this point in the experiment it has been so small that nobody bothered to include it. Energy gravitates. Mass and energy are the same quantity, and anything with energy curves the space-time around it. Every time you turn up the probe energy, you are also concentrating a larger amount of gravitating stuff into a smaller region, because the whole point is that the probe is getting more compact as it gets more energetic. Keep going, and you reach a threshold that Kip Thorne set out in 1972 in what is usually called the hoop conjecture. If you compress enough energy into a small enough region, small enough that a hoop of a particular size could be passed around it in every direction, a horizon forms, a black hole. And at the Planck scale, that is exactly what your probe does. Watch it happen. You raise the energy one more step, expecting the image to sharpen the way it has every time before. Instead, a horizon closes around the interaction region. Everything you were trying to look at is now inside it, and no information from inside a horizon reaches the outside. You have not photographed the target. You have buried it. So you do the natural thing, which is to push harder. And here is where the whole enterprise turns over on itself, because pushing harder makes it worse. A more energetic probe makes a heavier black hole, and a heavier black hole has a larger horizon. Every additional joule you spend hides a larger region than the one before. The resolution curve, which has been climbing steadily for 150 years from Abbe's microscope through X-rays and electrons and accelerators, reaches a maximum and turns downward. Its peak is at the Planck length. The black hole you just made does not even stay around to be studied. A black hole of 1 Planck mass is the lightest one that can exist, and it evaporates through Hawking radiation almost instantaneously, in roughly 1 Planck time. It is not an object. It is a flash of failure, appearing and disintegrating faster than any conceivable clock, leaving nothing behind but the fact that your instrument stopped working. There is an independent second road to the same conclusion, which is worth knowing about because two independent arguments landing on the same number is a much stronger situation than one. Heisenberg's uncertainty principle says that the more precisely you pin down a particle's position, the less precisely you know its momentum. Since the 1960s, various people, Chris Mead in 1964, and later a group of string theorists in 1989, have worked out what happens when you redo that argument, including the gravitational effect of the measuring probe itself. What comes out is a modified relation with an extra term, and the extra term does something the original does not. Instead of position uncertainty shrinking without limit as you increase momentum, it falls, reaches a minimum, and then starts to rise again. The minimum is of order the Planck length. A survey by Louis Garay in 1995 went through the various approaches and found the result to be remarkably insensitive to which model of quantum gravity you assume. So two quite different lines of reasoning, one from black hole formation, one from a modified uncertainty principle, both say the same thing. There is a shortest distance you can ask about, and it is the Planck length. There is an objection people raise at this point, and it deserves an answer rather than a dismissal. If space really has a smallest length, what happens when somebody moves? Special relativity says that lengths contract along the direction of motion for a fast-moving observer. So if I see a grain of space 1 Planck length across, and you fly past at close to the speed of light, you should see it contracted, shorter than the shortest possible length, which is a contradiction. This is a genuinely serious problem, and an entire research program called Doubly Special Relativity was built to solve it, by modifying the rules of relativity so that the Planck length is invariant the way the speed of light is. It works at the level of individual particles, and then it produces a well-known embarrassment nicknamed the soccer ball problem. Apply the modified rules to an ordinary macroscopic object made of many particles, and you get obviously wrong answers about how it behaves. The objection has not been cleanly answered, and it is one of the better reasons to be cautious about the grainy picture. Notice how carefully that has to be phrased. Not, there is a shortest distance. A shortest distance you can ask about. The argument is about the measuring operation, not about the fabric of the world. It says that the act of resolving a distance requires energy, that energy gravitates, and that past a certain point, the two requirements are in direct conflict with each other. Every method fails. Not this method, or current methods, every method, because the failure comes from the two most basic facts we have, that probing costs energy, and that energy curves space. And that is why this is a wall rather than a frontier. A frontier is somewhere you have not been yet. A wall is somewhere the road stops. The Large Hadron Collider is short of the Planck energy by a factor of 900 trillion, and that alone would be discouraging enough. But even if you solved the engineering, even with a machine the size of a galaxy, even with unlimited power, the last increment of energy would close a horizon around your answer, and you would end up further away than you started. That flea's egg from a few minutes ago, the weight you could not feel, is the mechanism. Concentrate it into a Planck volume, and it becomes a black hole, and the black hole is the reason nobody will ever see past this scale. Which leaves an obvious question, and it is the one everybody actually wants answered. If we cannot look, what do we think is there? Everything from here to the end of this part is speculation, and I want to label it clearly before we start, because the boundary between what is established and what is proposed gets blurred constantly in discussions of this subject, and it does nobody any favors. Nothing in this part has been observed. Nothing in it has been tested. These are the leading proposals from people who have spent careers on the problem, and they are serious, careful, mathematically detailed proposals. And they disagree with one another, not only about what is down there, but about whether the question has an answer at all. The oldest of them belongs to John Wheeler, who in 1955 suggested that at the Planck scale, space-time is not smooth in any sense. He called it quantum foam. The picture is that if you could look at a region of empty space at that resolution, you would find geometry itself fluctuating violently from moment to moment, curvature appearing and vanishing, and, in the more aggressive versions, the topology changing, with tiny handles and bridges forming and closing continuously. Not a lattice, not a grid, a churn. The reason the idea has stayed around for 70 years is that it follows from a fairly simple argument. Quantum mechanics says that any field that can fluctuate does. The more precisely you localize a region, the wilder the fluctuations in it. If gravity is quantum, then the gravitational field, which is the geometry, must fluctuate too, and at the Planck scale, the fluctuations become comparable to the geometry itself. Nobody has ever seen quantum foam. There is no complete formalism that describes it. It remains a picture rather than a theory. Loop quantum gravity goes considerably further and makes a specific, calculable claim. Space is genuinely granular, and the granularity can be computed. The central result came from Carlo Rovelli and Lee Smolin in 1995. In their formulation, geometric quantities like area and volume are not smooth continuous variables, but operators, in the same technical sense that energy is an operator in ordinary quantum mechanics. And just as the energy of an electron in an atom can only take certain discrete values, the area of a surface can only take certain discrete values. There is a smallest possible non-zero area, and it is of order the Planck area. There is a smallest non-zero volume. Space, in this picture, has atoms, in the strict sense, quantities of it that cannot be subdivided, and time behaves correspondingly. The network of relationships that constitutes space evolves in steps rather than flowing, which means that at the most fundamental level, the universe would be closer to a clock ticking than to a river running. There would be a genuine answer to how many moments have passed since the beginning. That is a bold claim, and it is not universally accepted, even within the field. Bianca Dittrich and Thomas Tiemann have argued that the discreteness result may be an artifact of a particular technical choice rather than a physical prediction, and Rovelli has argued back. It is an open technical dispute among specialists, not settled physics. String theory offers a different flavor of minimum length, and its version is subtler than either of the others. In string theory, the fundamental objects are not points, but extended strings, roughly Planck length in size. That already changes the microscope argument, because a point-like probe can in principle be aimed at a point-like target, and an extended probe cannot. But the deeper feature is what happens when you increase the energy. Fire more energy into a string, and it does not become a sharper probe. It becomes a longer one. The extra energy excites more vibrational modes, and the string spreads out. So beyond a certain point, pushing harder makes your instrument blunter in a very literal, physical sense. There is also a symmetry in string theory, called T-duality. And it is one of the strangest results in theoretical physics. If you curl up a dimension into a circle of radius r, the physics you get is exactly identical to the physics you get from a circle of a radius proportional to 1 divided by r. Not similar, indistinguishable, the same spectrum of particles, the same interactions, the same everything. Which means that smaller than the string scale is not a place you have failed to reach. It is a description of a world you have already described, under a different name. The question is not blocked, it is degenerate. Then there is asymptotic safety, which is the most conservative proposal on the list, and the one that says all of this may be a false alarm. The reason gravity gives infinities at high energy is that it is what physicists call non-renormalizable. The technique that tamed the infinities in quantum electrodynamics does not work on it, because every order of the calculation requires new parameters and the theory loses predictive power. But that verdict rests on a particular approximation, valid when the interaction is weak. Steven Weinberg suggested in the 1970s that if the strength of gravity, as it changes with energy, approaches a fixed value at high energies rather than growing without limit, then the theory would remain sensible and predictive all the way up, with no new physics required at all. There is a substantial research program pursuing this, with a fair amount of numerical evidence and no consensus. If asymptotic safety is right, then the Planck scale is not really a wall at all. It is a crossover, a change of behavior, the way water changes behavior at 100 degrees, without anything mysterious happening to the molecules. And there is one more possibility, which is the one I find hardest to hold in mind for more than a few seconds at a time. If gravity is quantum, then geometry can be in superposition. That is not an exotic add-on, it is what quantizing something means. An electron can be in a superposition of two positions, and if the gravitational field is quantum, then the shape of spacetime can be in a superposition of two shapes, which means the causal structure, the question of which events can influence which, what is before what is even in principle able to reach what, would be indefinite. Not unknown. Indefinite, in the way an electron's position is indefinite rather than merely unmeasured. There are experimental proposals to test whether gravity is quantum in this sense, using pairs of tiny masses in superposition and looking for gravitationally mediated entanglement between them. They are ingenious, and they are extraordinarily hard, and they operate around 30 orders of magnitude away from the Planck scale. Even if they succeed, they would tell us that gravity is quantum. They would not tell us what happens down there. It would be unfair to leave the impression that none of this has ever been tested, because one class of prediction has been, and the result is worth knowing. If the vacuum were granular in certain ways, light of different energies would travel through it at very slightly different speeds. The graininess would affect a short wavelength photon differently from a long wavelength one. Over a meter, or a kilometer, or the width of a solar system, the difference would be far too small to detect. But gamma-ray bursts occur billions of light-years away, and release photons across an enormous range of energies within a fraction of a second. After a journey of that length, even an unimaginably small difference in speed would separate the arrival times measurably. Observatories including the Fermi Space Telescope and the Integral mission have looked. The photons arrive together. The constraints from that work now exclude some categories of energy-dependent vacuum behavior at and even beyond the Planck energy, which is a genuinely surprising experimental reach for a scale we cannot approach in any other way. It does not rule out granularity in general. Many models predict no such effect at all. But it is a real test, and it came back negative, and that is worth more than any amount of argument. There is also the holographic principle sitting underneath this whole discussion, and it complicates the picture in a useful way. It emerged from black hole thermodynamics, and it says that the maximum amount of information you can pack into a region of space is proportional not to the volume of the region, but to the area of its boundary. counted in Planck areas. If that is right, and a great many theorists think it is, then the naive picture of the Planck scale, in which you imagine space filled with a three-dimensional grid of tiny cells each carrying its own information, dramatically overcounts. The degrees of freedom are somehow on the surface, not in the bulk, which suggests that the whole intuition of what is it made of down there may be asking about the wrong dimension. So step back and look at that list. Quantum foam says the geometry churns. Loop quantum gravity says space has atoms. String theory says the question folds back on itself. Asymptotic safety says nothing special happens, and we have been alarmed over an artifact of our approximations. Superposed geometry says the question of what is where may not have a definite answer. Those are not variations on a theme. They are fundamentally different claims about the nature of the world, and after 70 years of extremely hard work by extremely capable people, there is no experiment that distinguishes between them. And notice something about the whole set. Every one of these proposals arrives at the Planck scale because of the same three constants. Change the value of the gravitational constant, and every one of these theories relocates its predictions accordingly. They disagree about everything except where the disagreement happens, and that location was fixed in 1899 by cancelling units, which is where Planck's own sentence comes back with a weight he never intended. He said his units would retain their meaning for all times and for all civilizations, even extraterrestrial and non-human ones. He was right, and the rightness is the problem. Any physicist anywhere, on any world, working from those same three constants, arrives at the same length and the same time and the same wall. This is not a limitation of human instruments or human mathematics or the particular history that produced our theories. A species that had never had a Newton or an Einstein, that reached physics by an entirely different route, would still find the arithmetic pointing at the same place, and would still find their equations failing there. Whatever this boundary is, it is not ours. It belongs to everyone. Which brings us to the question underneath all of it. Not what is down there, but why those numbers, and not others. We have arrived back at the list. 24 numbers, measured and not explained. 4 of them describing the arena rather than its contents. 3 of those 4 combining into a scale that marks the end of what we can calculate. And underneath all of it, the question that has been sitting in the room since the first minute of this video: why those values? There is a whole literature attached to this question, and a great deal of heat, and I want to go through it carefully, because it is a subject where it is easy to be sloppy in either direction. The observation that starts it is this. Several of the constants appear to sit in narrow bands, in the sense that if you change them by a modest amount and work out what kind of universe results, you do not get a different universe with different physics. You get a universe with nothing in it worth mentioning. Some standard examples. If the strong nuclear force were a few % stronger, hydrogen would fuse into diprotons rather than deuterium, and stars would burn through their fuel in a way that leaves no long-lived main sequence. A few % weaker, and deuterium does not bind at all, which shuts down the first step of stellar fusion entirely. If the difference between the neutron and proton masses were somewhat different, either free protons would decay into neutrons, or neutrons would be stable enough to swallow the hydrogen supply. The classic case is Fred Hoyle's, who in 1953 reasoned that carbon could only be produced in stars in useful quantities if the carbon-12 nucleus had an energy level in a very specific place, around 7.65 million electron volts, and told experimentalists to go and look for it. They found it. Carbon exists because that resonance sits where it does, and you are made of carbon. The Hoyle case is also a good illustration of how these arguments get overstated in the retelling, and it is worth being accurate about. Hoyle's prediction was a genuine triumph of reasoning, and the resonance is genuinely required for carbon production. But the popular version, in which shifting the resonance by a fraction of a percent would erase all carbon from the universe, is tighter than the calculations support. Later work found the tolerance to be wider, and there is a compensating effect in oxygen production that partly offsets the change. The case survives. It survives smaller than it is usually presented. The most extreme case is the cosmological constant, and it is worth its own explanation, because the number involved is beyond any comparison in the rest of science. Quantum field theory says empty space is not empty. Every field in the universe has fluctuations even in its lowest energy state, and those fluctuations carry energy, and by general relativity, all energy gravitates, so you can calculate what the vacuum energy density of empty space should be by adding up the contributions of the fields up to some maximum energy scale. Do that calculation with the Planck scale as the cutoff, which is the natural thing to do because that is where the theory stops working, and you get a value that is larger than what is actually observed by roughly 120 orders of magnitude, 10 to the 120. That is a 1 with 120 zeros after it. It is frequently called the worst prediction in the history of physics, and the description is not really hyperbole. Steven Weinberg's review of the problem, published in 1989, laid out the situation, and it has not improved in the decades since. What is observed instead is a very small positive value, the dark energy that was detected in 1998, and that is currently accelerating the expansion of the universe. So whatever mechanism cancels that enormous theoretical prediction cancels it to 120 decimal places, and then stops, leaving a residue. Nobody knows what the mechanism is, and if the residue were substantially larger, the universe would have pulled itself apart before galaxies could form. That last point is the one place in this entire discussion where anthropic reasoning made a prediction in advance rather than after the fact. In 1987, in a paper in Physical Review Letters, Weinberg argued that if the value of the cosmological constant varied across some larger ensemble of universes, then observers could only exist in those where it was small enough for galaxies to form, and he calculated an upper bound. When the acceleration was measured 11 years later, the value fell within his range. That is not proof of anything. It is the strongest card the anthropic argument has, and it is a real card. So what do people make of all this? Broadly, 3 answers, and none of them can currently be tested. The first is design. If the numbers appear tuned, perhaps they were tuned by something with an intention. This is an old argument in a new costume, and it is taken seriously enough in the literature to be argued about properly. Luke Barnes published a lengthy review in 2012, surveying the claimed cases and defending them against Victor Stenger's book, The Fallacy of Fine-Tuning, which argues that the tuning is largely an artifact of how the cases are set up. The second is the multiverse. If there are enormously many universes with different values of the constants, then somewhere among them there are universes that permit complexity, and it is unsurprising that anyone asking this question finds themselves in one. The string landscape, with its 10 to the 500th possible configurations, provides a natural mechanism, and eternal inflation provides a way to realize them. The third is simulation. If the constants must be entered by hand, that is precisely what you would do to configure a program, and if the Planck length is a smallest unit, that looks like a resolution setting. Nick Bostrom's paper from 2003 made a careful statistical version of this argument, and it is worth noting that his actual argument is a trilemma about the ratio of simulated to real observers, not a claim about physics at all. Now let me give you the counter-arguments, because they are strong and they are usually left out. On tuning, almost every fine-tuning case is calculated by varying one constant while holding all the others fixed. There is no reason to expect that to be representative. Some studies that vary several at once find substantially wider habitable regions of parameter space than the classic one-at-a-time estimates suggest. On probability, to say that a value is improbable, you need a probability distribution, and we have exactly one universe to sample. We do not know the range the constants could have taken, or whether they could have taken any other value at all. A number that could only ever have been what it is has a probability of 1. On tuning for life specifically, if the universe were tuned for life, it is a strange piece of work. Essentially, all of it is lethal. Empty vacuum, radiation, gravitational wells. The habitable fraction is so close to zero that describing the whole arrangement as designed for the purpose requires ignoring almost everything in it. On the simulation claim specifically, the physics half of it is weaker than it sounds. The Planck length is not established to be a lattice spacing. A fundamental spatial lattice is in real tension with the relativity tests we discussed earlier, and there has been a serious experimental search. Craig Hogan proposed a specific model of Planck scale spacetime indeterminacy that would produce a detectable correlated jitter in a sufficiently sensitive interferometer. Some unexplained noise in the GO 600 gravitational wave detector in the late 2000s was briefly and loudly reported as a possible detection. So the holometer was built at Fermilab, specifically to look, and its results, published in 2015 and 2017, excluded the model. That is exactly how it is supposed to go. A speculative idea about the Planck scale was turned into a number, the number was measured, and the idea was killed within a decade. And the crucial point, which applies to all three answers equally, none of them is currently falsifiable. There is no experiment that distinguishes a designed universe from a multiverse, from a simulation, from a brute fact. People who dismiss the design argument as unscientific while accepting the multiverse are applying the standard unevenly, and people who do the reverse are doing the same thing in the other direction. It is worth asking what a real answer would even look like, because that clarifies how far away we are. A successful explanation of the constants would be a theory with no adjustable inputs at all, from which the electron mass and the fine structure constant and all the rest emerge as consequences, the way the ratio of a circle's circumference to its diameter emerges from geometry rather than being measured. Nobody has produced anything remotely like that. And here is the difficulty. Any such theory would have to be formulated at the scale where the structure lives, and every indication is that the structure lives at or near the Planck scale, which is the one place we have just spent an hour establishing that we cannot reach, and cannot reach for reasons that appear to be fundamental rather than technological, which leaves us in an honest but uncomfortable position, and I think it is worth saying plainly. Something happened. 24 numbers landed in the narrow ranges that permit atoms, chemistry, structure, stars, and a species capable of noticing. That much is not in dispute by anyone. What is in dispute is what it means. And the honest answer is that we cannot say because we have one sample, no distribution, and no test. We appear to have won something. Nobody can tell us how many tickets were sold, or whether there was a draw at all. And that, finally, is where the two halves of tonight's question meet. At the beginning of tonight, I asked you to imagine building a universe, and I said that before you could press run, you would need a short list of numbers that no theory produces, the numbers you would have to type in by hand. I want to give you the answer to the question we have been carrying since then, because it is time, and because it is not any of the three possibilities I offered at the start. Our understanding of physics has a limit, and we cannot explain it, and the reason we cannot explain it is that the limit is made of the same material as the foundation. Here is the shape of it, plainly. Physics has two ends. At one end are the inputs, about 24 numbers that have to be measured and entered before anything can be calculated, and that 100 years of the best theoretical work in the history of the subject has failed to derive. At the other end is the output, a scale, arrived at by nothing more than cancelling the units of three of those same numbers against each other, at which every calculation we know how to perform returns infinity. And those are not two separate problems that happen to sit at opposite ends of the subject. They are the same problem, seen from two directions. The wall at the bottom of physics is not made of some exotic substance we have failed to identify. It is made of the gravitational constant, the speed of light, and the Planck constant. Three of the numbers off the list. The reason we cannot say where the boundary comes from is precisely the reason we cannot say where the electron's mass comes from, because it is the same kind of ignorance, about the same kind of quantity, and there is no more explanation available for one than for the other. Turn it around, and it gets sharper. The reason the boundary sits at 10 to the minus 35 meters rather than somewhere we could reach is that the gravitational constant has the value it has, and gravity is therefore weak by a factor of 10 to the 36, and the energy required to look at that scale is therefore concentrated enough to become a black hole. If G were larger, the wall would be closer and possibly reachable. We are locked out of the answer by the size of a number we cannot explain, and the answer we are locked out of is very probably the explanation of that number. That is the circle, and I do not think there is a way out of it from where we are standing. To explain the constants, you would need physics at the scale the constants define. To reach that scale, you would need a probe that hides its target the moment it becomes sharp enough to see it. It also explains something that has probably been nagging at you for the last hour, which is why the two great problems in modern physics both take the same peculiar shape. The hierarchy problem asks why the Higgs mass is 16 orders of magnitude below the Planck scale. The cosmological constant problem asks why the vacuum energy is 120 orders of magnitude below what the Planck scale suggests. Both are complaints about a distance from the same wall. Both are, at bottom, questions about the same three constants. The two largest unsolved problems in the subject are not separate mysteries. They are two people standing at different points along the same unexplained edge, asking why they are so far from it. So what kind of limit is this, actually? There were 3 readings, and they are all still open, and it is worth restating them, now that we know what they are readings of. It might be a real flaw. Space and time may genuinely be granular below this scale, with a smallest area and a smallest volume, and the smoothness we take for granted is an approximation, the way the smoothness of water is an approximation. Loop quantum gravity says so, and calculates it. Nobody has confirmed it. It might be a limit on us, rather than on the world. Nothing may change at all down there. The continuum may run on forever, and what fails is only the operation of asking. On this reading, the boundary is epistemic. It is a fact about the reach of measurement, and it is the reading that the black hole argument most directly supports, and it is the more conservative of the two. Or it might be neither, and it might be a crossover. Every theory in physics is valid over a range and expires outside it, and the Planck scale may simply be where our current description hands over to a better one that will describe what happens there in perfectly ordinary language. That has happened before. In 1899, the interior of the atom was as unreachable as this, and for much the same reasons, and 30 years later it was undergraduate material. I find I cannot choose between them, and I am fairly confident that is the correct state to be in, because nothing currently distinguishes them, and that is a genuinely unusual place for physics to be. A subject that can specify the location of its own boundary to 5 decimal places, and cannot say what kind of thing the boundary is. There is one more thing worth carrying away, and it is about the shape of not knowing. Most of what we do not know is ordinary. We do not know what dark matter is made of, but the question is well posed, and somebody may answer it while you are alive. Those are gaps in the map, and gaps get filled. What sits at the Planck scale is not a gap in the map. It is the place where the map stops being a map. where the words we are using to ask, the before and the smaller and the where, are themselves outputs of the theory rather than inputs to it, and asking to use them outside the range where the theory works may be as meaningless as asking what is north of the North Pole. And there is a small, quiet thing about all of this that I keep returning to, which is the flea's egg. Of every quantity at the bottom of physics, one is human-sized. 21.76 micrograms, a weight you could not feel, a speck you could hold on a fingertip without knowing it was there. It is not an accident that this particular one is the one you could touch. It is human-sized because gravity is weak, and gravity being weak is the reason the wall is where it is, which is the reason we are locked out. The one number at the bottom of physics that you could actually pick up is the number that guarantees you will never get past it. I do not find that discouraging, and I have thought about it for a long time. There is something in it that seems to me closer to relief than to frustration. Because consider what has actually been achieved here. A man in a lecture room in Berlin, in the last spring of the 19th century, with no quantum mechanics, and no relativity, and no idea what he was doing, took 3 measured numbers and cancelled their units against one another. And in doing so he located, correctly, to 5 decimal places, the exact place where everything his century, and the next one would build, was going to stop working. He did it as an afterthought, on the last 3 pages of a paper about hot objects, and then he went back to worrying about radiation. We have found the edge of our own understanding, and we have measured it precisely, and we can say honestly and specifically what we do not know and why we cannot currently know it. That is not the same as ignorance. Ignorance does not come with error bars. Not knowing something, and knowing precisely what it is you do not know, and exactly why you cannot currently know it, are separated by about 400 years of very patient work. So the next time you pick something up, a cup, a phone, the corner of a blanket, remember that the reason it holds together, the reason it has the weight it has, and the color it has, and the solidity it has, comes down to about 24 numbers that nobody chose and nobody can explain. And remember that if you kept looking closer, past the molecules and the atoms and the nucleus and the quarks, and kept going for another 20 orders of magnitude through absolutely nothing at all, you would arrive at a place built out of 3 of those same numbers, where physics simply stops having anything more to say. It is under everything. It has been there the entire time, and it is the one part of the universe that has never been seen, and, as far as anybody can currently tell, never will be. Thank you for spending this long night at the bottom of physics with me. If this slow way around a very large question is how you like to fall asleep, a like or subscribe would mean a great deal. It is a small thing for you, and it helps me keep making these. And remember, the next time you set something down, and it stays where you put it, that the reason is a number nobody has ever explained. Good night, and may you never look at the space between things the same way again.